Let's learn about the characteristics and basic operating structure of each type of transistor. Let's learn about the operating structure of a bipolar transistor. The name transistor is a combination of the words transfer and resistor, meaning transfer resistance or transformation resistance, and refers to a resistance element that can be changed by some control. A bipolar transistor is a three-terminal device, with the collector and emitter forming a channel through which a large current flows. And the base is the terminal that controls the amount of current flowing in the channel between the collector and emitter. It is a structure in which a large amount of current is controlled by changing the resistance value between the collector and emitter by applying a small current to the base. That is, like the valve on the right, when current is applied to the base and the valve is completely closed, there is no current between the channels, so it is in the off state, that is, the cut-off state. Conversely, when the valve is completely opened, current is conducted and it is in the on state, that is, the saturation state. This on-off control is called the switching action of the transistor. When the base current is applied to an appropriate size and the valve is halfway open, turning the valve slightly to the left and right causes the large current in the channel to vary linearly, thus amplifying the current. This state is called active. The switching operation utilizes two states, cutoff and saturation, and the amplification operation operates in the active state. The design of these three states is determined by the base current and the biasing of the collector and emitter. In this way, a bipolar transistor can be viewed as a transfer resistor that controls the flow of large current by varying the resistance value between the collector and emitter by controlling a small base current. This is the working structure of the preceding bipolar transistor, and we will learn about another type of transistor, the MOSFET. MOSFET is an abbreviation for metal oxide semiconductor field effect transistor. MOSFET is a three-terminal device, where the drain and source form a channel through which a large current flows. And the gate is the terminal that controls the amount of current flowing in the channel between the drain and the source. The structure is such that the resistance value between the drain and the source changes by a small voltage applied to the gate, thereby adjusting the large amount of current in the channel between the drain and the source. The difference from a bipolar transistor is that the channel is controlled, that is, turned on and off, by the gate voltage. Like the valve on the right, when voltage is applied to the gate and the valve is fully opened, the current flows and it becomes the on state, and when the voltage at the gate is zero, the channel is completely closed and there is no current between the channels, so it becomes the off state. This on-off control is called the switching action of the MOSFET. It is important to remember that while bipolar transistors adjust their channel resistance by applying current to the base, MOSFETs are controlled by applying voltage to the gate. The main difference is that bipolar transistors are current-driven and MOSFETs are voltage-driven. MOSFETs are more widely used for switching large current capacities due to the presence of a turn-on voltage between the collector and emitter that form the bipolar transistor channel. Both devices can be viewed as three-terminal switches that conduct or block current between channels with a small control signal, that is, current or voltage. However, unlike general switches, it is important to note that a large channel current is controlled in only one direction depending on the properties of the semiconductor switch. And therefore bipolar transistors are classified into NPN and PNP depending on the direction of the channel current, and MOSFETs are classified into NMOS and P-type MOSFETs. Of course, the polarity of the control current or voltage also changes at this time. Bipolar transistors come in two types, NPN and PNP. The directions of the base control current and channel current are opposite to each other, and the NPN type has a structure in which the channel current flows from the collector to the emitter when current enters the base, while the PNP type has a structure in which the channel current flows from the emitter to the collector when current exits the base. Here, the way to distinguish NPN and PNP is based on the arrow on the emitter side. Just like a diode, the current flows in the direction of the arrow, so the base side is P and the emitter side is N. Therefore, the remaining collector will be N, so it becomes an NPN, and if the base side control current also flows to the base side as in the direction of the arrow. The channel current is a structure in which a large channel current flows from the collector to the emitter in the direction of the arrow. The PNP type on the right has an arrow pointing from the emitter to the base, so the emitter is P, the base is N, and the remaining collector is P, so it becomes a PNP, and contrary to the NPN. When the base side control current flows out to the base in the direction of the arrow. The channel current is a structure in which a large channel current flows from the emitter to the collector in the direction of the arrow. In this way, if you intuitively understand the direction of the control current and the direction of the channel current based on the arrows on the symbols of NPN and PNP transistors, it will be very helpful for circuit analysis. In other words, in the case of the NPN, the channel current flows from the collector to the emitter due to the current input to the base. And in the case of the PNP, the channel current flows from the emitter to the collector due to the current flowing out of the base. At this time, the direction of the control current is determined by the voltage, so to turn on the NPN, you apply a high voltage to the base, and to turn on the PNP, you apply a low voltage to the base. Compared to bipolar transistors, MOSFETs have a complex symbol structure. It consists of three terminals, the gate, which is the control terminal, and the drain and source that form the channel. The channel through which a large current flows is the three vertical bars in the middle of the symbol. And the fact that they are spaced apart at regular intervals means that when the gate is left floating without an input voltage, the default is off. When voltage is applied to the gate, the three vertical bars are connected, allowing current to flow. There are two types of MOSFETs, NMOS and P-type MOSFET, and the directions of the gate control voltage and channel current are opposite to each other. In other words, NMOS has a structure in which the channel current flows from the drain to the source when the voltage between the gate and the source is positive. And P-type MOSFET has a structure in which the channel current flows from the source to the drain when the voltage between the gate and the source is negative. You can distinguish NMOS and P-type MOSFETs by looking at the arrow on the source side. The NMOS on the left has an arrow pointing to the channel, so the source side is P and the channel side is N, making it an N-channel MOSFET, or NMOS. The P-type MOSFET on the right has an arrow starting at the channel, so the channel side is P and the source side is N, making it a P-channel MOSFET, or P-type MOSFET. Transistors are classified into bipolar transistors, MOSFETs, and IGBTs depending on their structure and operation method. All three of these are switching elements that change the resistance value between channels by the current or voltage of the control terminal, thereby turning them on and off. Bipolar transistors can also perform amplification, but recently they have been replaced by dedicated ICs or op-amps, and are mostly used for switching purposes. Depending on the allowable power, they are classified into small signal and power types, and are classified into small signal types of less than 1 watt and power types of 1 watt or more. Depending on the mounting type, they are also classified into lead type and SMT type. And bipolar transistors are classified into NPN and PNP, and MOSFETs are divided into NMOS and P-type MOSFETs. IGBT is a hybrid structure of MOSFET and bipolar transistor that has the voltage control structure of MOSFET and the channel structure of bipolar transistor. In other words, it has the characteristic of utilizing the advantages of both devices. IGBT is an abbreviation for insulated gate bipolar transistor and is called an insulated gate type bipolar transistor. It is mainly used as a high voltage, high current switching device such as a high power inverter. Let's compare the characteristics of three types of transistors: bipolar transistors, MOSFETs, and IGBTs. First, looking at the driving method, we can see that the bipolar transistor is controlled by the base current, and the MOSFET and IGBT are driven by the gate voltage because they have an insulating structure where the gate is separated from the channel. In terms of driving power, the IGBT is the largest, followed by the bipolar transistor and then the MOSFET. The switching speed of MOSFET is the fastest, followed by IGBT and bipolar transistor. In terms of price, the IGBT for high power is obviously the most expensive, followed by MOSFETs and bipolar transistors. And the unit price of each component may vary depending on the rating or application. If we look at the actual driving circuit, the bipolar transistor is a current drive switching element that turns on and off depending on the direction of the current applied to the base. It is divided into the NPN method that turns on between C and E when current is input to the base, and the PNP method that turns on between E and C when current is extracted from the base. The directions of the control current and turn-on current of these two methods are the same as the direction of the arrow between the base and the emitter. So they can be intuitively understood just by looking at the element symbols. In other words, since the arrow in the NPN points from the base to the emitter, when the base current is input in the direction of the arrow, the channel current also flows from the collector to the emitter in the direction of the arrow. Since the arrow in the PNP points from the emitter to the base, when the current flows out of the base in the direction of the arrow, the channel current also flows from the emitter to the collector in the direction of the arrow. In the NPN, when the control input voltage is high, current flows into the base, turning on the channel between C and E. When the control input voltage is low, the current in the base becomes zero, turning off the channel between C and E in the PNP. On the contrary, when the control input voltage is low, current flows out of the base, turning on the channel between E and C. When the control input voltage is high, the current in the base becomes zero, turning off the channel. Here, it should be noted that the PNP must have the same control voltage level and VCC power supply voltage. For example, if VCC is 5 volts, the control voltage must also be 5-volt logic. If VCC is 12 volts and the control voltage is 5 volts, the control voltage will always be on whether it is low or high, and control will not be possible. In this case, an additional circuit is required. NPN does not have such special restrictions, but the base control current amount requires tuning in the circuit. Another thing to remember here is that for both NPN and PNP, the load, i.e. the element to be driven, must be connected to the collector terminal. Why is that? Because the control current is determined by the voltage conditions between the base and the emitter. If a load is connected to the emitter side, the appropriate base side control current adjustment is impossible, so the load is configured to the collector terminal, which is a terminal independent of the control current. MOSFET is a voltage-driven switching device that turns on and off depending on the voltage applied to the gate. It is divided into NMOS, which turns on when high is applied between the gate and source, and P-type MOSFET, which turns on when low is applied between the gate and source, and the source and drain. The direction of the control voltage and turn-on current of these two types is somewhat difficult to intuitively understand with just the component symbols. So first determine whether it is N-channel or P-channel, and then recognize that NMOS has equivalent channel current characteristics to NPN and P-type MOSFET has equivalent channel current characteristics to PNP. Then, Simply remember that the control method is voltage. That is, since the MOSFET and bipolar transistor are matched in terms of drain and collector, source and emitter, and gate and base. It is possible to understand the operation of the MOSFET intuitively if you understand it based on this. The NMOS is equivalent to the NPN, so when high is input to the gate, the drain and source are turned on, and the channel current flows to drive the load, and the P-type MOSFET is equivalent to the PNP, so when low is input to the gate, the source and drain are turned on, and the channel current flows to drive the load. If you look at the actual driving circuit, when the control input voltage of the NMOS is high, the voltage between the gate and the source, the VGS, becomes positive, turning on the channel between the drain and the source, and when the control input voltage is low, the VGS becomes zero, turning off the channel between the drain and the source. In contrast, the P-type MOSFET turns on when the control input voltage is low. The voltage between the gate and source, VGS, becomes negative, and the channel between the source and drain is turned on. When the control input voltage is high, the VGS becomes zero, and the channel between the source and drain is turned off. At this time, the reference voltage between the gate and source for on and off, VGS, is specified as the threshold voltage, VTH, in the specifications. And the gate applied voltage can be determined based on this voltage. Like bipolar, P-type MOSFETs require that the control voltage level and the VCC power supply voltage be the same. For example, if VCC is 5 volts, the control voltage must also be 5 volts logic. If VCC is 12 volts and the control voltage is 5 volts, the control voltage will always be on whether the control voltage is low or high, which makes it impossible to control, and in this case, additional circuitry is required. NMOS does not have such special restrictions, but the control voltage must be applied higher than the threshold voltage, VTH, according to the specifications. And, like bipolar, all loads, that is, the elements to be driven, must be connected to the drain terminal. Why is that? Because the control voltage is determined by the voltage conditions between the gate and the source, if a load is connected to the source side. The appropriate gate side control voltage adjustment is impossible, so the load is configured at the drain terminal, which is a terminal independent of the control voltage. This time, let's learn about the concept of low side and high side switches. For external loads, placing the semiconductor switch on the ground side is called low side driving, and placing it on the power side is called high side driving. Low side driving method is a commonly used method, and since the control input voltage or current is applied with respect to the ground, NPN or NMOS is applied. And it is an active high method that turns on when the control input is high. On the other hand, the high side driving method is an active low method in which the control input voltage or current is applied based on the power supply voltage. So a PNP or P-type MOSFET is applied, and it turns on when the control input is low. For loads that use multiple power supply voltages, a low side switch is appropriate. For loads that use the same power supply voltage, a high side switch is appropriate. As explained above, low side driving determines the control current or voltage with respect to ground, so the switching circuit is configured with NPN or NMOS. Since high side driving determines the control current or voltage based on the power supply voltage, the switching circuit is configured with a PNP or P-type MOSFET. H-bridge is a circuit that combines a low side switch and a high side switch and is suitable for loads that require forward and reverse current, such as motors or Peltier elements. The structure is such that the high side switch is placed on the top of the H-bridge and the low side switch is placed on the bottom. When current flows from left to right through the load, the upper left switch and the lower right switch are turned on simultaneously to form a current path. when current flows from right to left through the load. The upper right switch and the lower left switch are turned on simultaneously to form a current path.